Welcome to the library. Imagine a system that can retrieve any book in milliseconds, but instead of reading them, it just violently hurls them into a pile and hopes the answer is somewhere in the wreckage. That chaos is what happens under the hood of a poorly designed AI system. Let's look at a concrete engineering scenario: an internal developer querying a codebase using a standard retrieval augmented generation, or RAG, setup. A developer submits a simple prompt: show me the fallback logic for the new V2 authentication API. The system fires back instantly. It delivers a highly confident, perfectly formatted block of code. It looks correct, but it will break production. The fatal error is in the context. The language model isn't citing the V2 API at all. It's pulling deprecated V1 authentication logic from a completely different project branch. To see why this happened, we have to look at the data flow. On the left is our query and the incorrect output. On the right is the retrieved context debug window, showing the raw code snippets the system actually fetched. Notice the highlighted text in those raw snippets. The chunks the system retrieved contain exact keyword matches for the phrases fallback logic and authentication. This creates a trap. The text it pulled is semantically similar to the developer's prompt. It's the right subject, but chronologically and factually it is useless. This highlights the core limitation. A system can perfectly map semantic meaning while still failing a basic logic test. This architecture, Retrieval Augmented Generation, or Basic RAG, is the single most deployed architectural pattern in production AI today. The theory behind it is elegant: look up the answer before you speak. But as we just saw, naive implementations of this pattern guarantee hallucinations. Treating semantic similarity as a proxy for factual accuracy turns a working prototype into a production catastrophe. Solving this requires a complete deconstruction of the pipeline. This diagram shows the two-phase state machine of Basic RAG, an offline indexing phase on the left and a real-time query phase on the right. Let's focus entirely on the indexing phase, where we load our raw knowledge base, PDFs, wikis, and code repositories. Once loaded, the documents undergo their first transformation: chunking. The system breaks these massive files into smaller, retrieval-sized pieces. We slice the text because embedding models have strict token limits, functioning best with passages of 256 to 512 tokens. Those chunks are then fed into the embedding model. This is the mechanism we use to translate text into meaning. Embeddings are algorithms that convert passages of text into numerical arrays, or vectors. These vectors are typically lists of numbers between 768 and 1536 dimensions long. The core rule relies on spatial relationships. Concepts with similar semantic meanings produce vectors that map very closely to each other in this high-dimensional space. For example, the phrases "forgot password" and "reset credentials" share almost no exact words. Yet, because their underlying intent is the same, they map to nearly identical mathematical coordinates. The specific embedding model you choose, whether it's OpenAI, Cohere, or an open-source option, dictates exactly how this spatial mapping occurs. It is a massive factor in your final retrieval quality. Once the text is converted into numbers, those vectors need a place to live. The final destination in the indexing phase is the vector store. Despite the hype, a vector store is merely a specialized database. It is explicitly designed to hold and search these massive numerical arrays efficiently. Notice that this entire process, loading, chunking, embedding, and storing, happens strictly before any user ever interacts with the system. Indexing is the act of translating human context into a mathematical topography that a machine can navigate. Now we move to the real-time query phase, the path from a user prompt to the final output. The first action intercepts the user's live question and embeds it, using the exact same model we used during indexing. Converted into a vector, the system performs a cosine similarity search, measuring the mathematical distance between the query and every document vector in the database. It retrieves the top K, usually the 3 to 10 most relevant passages. These retrieved text chunks are then stuffed directly into the language model's context window, right alongside the original user prompt. At this instance, and generates its final answer. It is strictly instructed to ground its response in the injected text, rather than relying on the weights it memorized during training. This pipeline is what bridges the gap between static, frozen model weights and dynamic, up-to-date data. Basic RAG doesn't teach a model new facts. It forces the model to read a targeted dossier before speaking. Let's pivot back to the code-base failure from Act 1 and identify the root cause in the pipeline. The hallucination was not caused by a weak embedding model. It also wasn't a slow or inaccurate database search. The search executed perfectly. The true point of failure happened offline. The visual here illustrates a naive chunking strategy. This specific method is fixed-size chunking. It is the simplest to implement, the most common in tutorials, and the most destructive approach to context. When you split text purely based on an arbitrary token limit, you inevitably cut mid-sentence, mid-thought, or right through the middle of a vital code block. The surrounding metadata that gives the text its meaning is destroyed. A perfectly embedded fragment of a broken sentence will still map accurately in vector space, but when it gets injected into the LLM prompt, it is practically useless for generating a coherent answer. A smarter fallback is recursive character splitting, which is standard in frameworks like LangChain. It actively tries to split text on natural paragraph and sentence boundaries, but prioritizing strict token counts over organic semantic boundaries guarantees the retrieval of fractured, useless context. There is an engineering solution to this bottleneck. This visualization illustrates the sentence window pattern. It utilizes a two-layer approach. The first layer creates microchunks at the individual sentence level for precise vector embedding. The second layer attaches metadata to that microchunk. This metadata links the precise single sentence back to a macro window of the 5 to 10 sentences immediately surrounding it in the original document. During query execution, the vector search targets and matches the exact microchunk, but instead of returning just the single sentence, the system retrieves and injects the entire macro window into the LLM context. Decoupling the embedding unit from the retrieval unit allows the system to combine granular mathematical matches with the full surrounding context. This leads to a common professional misconception regarding vector stores like Faiz, Chroma, Pinecone, or Qdrant. Choosing between a local library and a fully managed cloud solution is purely an operational scaling decision. It is not a fix for retrieval quality. If your chunking strategy is bad, your database choice will not save you. Which brings us to the final boundary of basic RAG. The architecture inherently lacks logical reasoning over its own retrieval step. A single cosine similarity search retrieves text based on distance. It cannot handle multi-step logical queries, complex data aggregations, or cross-referencing disparate sources. A perfectly chunked RAG pipeline is the necessary foundation of production AI. But evolving past simple search requires moving beyond single-pass retrieval and stepping into intelligent, agentic routing.